Good day, everyone. So far as I see, only 3 people are attending this lecture. So the topic of today's lecture would continue what we have started during the previous lecture, but it would be not a mathematically centered lecture, but rather we would discuss the properties of the physical system. And for today, we have Maxwell distribution. Maxwell's distribution. And this is a part of basics of gas kinetics. So what we actually study is the kinetic theory of gas, and in particular the distribution for velocities of the gas. So probably I think we should start with the consideration of why the distribution of velocities is so important. So why do we actually need to know how the velocities of molecules of gas are actually distributed? So we'll start with considering a container which has gas molecules which move at arbitrary velocities with different speeds and directions. And first of all, I think we should derive how pressure of the gas, so how pressure depends on the velocity distribution. If you look closer at the formulation of this problem, which I have written on the blackboard, you see that actually what we aim to find is the relationship between some macroscopic property of gas, which is pressure, and some microscopic quantities, which is the distribution for velocities of the gas. And in a certain way, I can say that actually this problem is one of the main problems related to statistical physics and kinetic theories in particular, because typically when we study some systems which contain many different particles, we understand how these particles move, how they interact with each other. And based on this knowledge, which is called microscopic properties of the system, we want to determine some macroscopic observable properties of your system. So usually you don't have any kind of an apparatus which can measure the velocity of gas particles with a small number of exceptions. But typically what you have is some measurement appliances which can measure the pressure, the volume, and other macroscopic properties of the system, like temperature too. So it's very important to have some kind of a procedure which allows you to establish the relationship between microscopic and macroscopic properties. And actually the second part of our course is devoted exactly to this problem. We want to understand the microscopic properties and their relationship with macroscopic. So here we start with one of the simplest problem in this of this type, and we want to determine how pressure depends on the velocity distribution. So first of all, we would like to consider a part of the side wall of this container. So what we see here is there are some particles which move at different velocities, and in particular, actually the pressure could be is mostly determined by an x projection of velocity, because if you have some kind of a motion which is parallel to the side wall of the container, then mostly the result of the collision of the gas particle with this container is almost independent from this parallel component of the velocity. So what we are mainly interested in is how actually the normal component of velocity and normal component of each gas molecule momenta changes with each collision. So let's say we draw this imaginary, let's say imaginary plane, which is slightly displaced from the actual side wall of the vessel, and we aim to find the quantity which I would call the flow of the momentum through this area. So what it means actually? So if the gas particle starts from here and then crosses our imaginary plane, so it now is here, then we can say that the momentum of all particles which are located in between this imaginary plane and the actual side wall of the container has increased by a certain amount. And you can say that the increment of that momentum is actually equal to px, which is the mass of the gas molecule multiplied by this particular gas molecule x component of velocity. So when it crosses this imaginary plane. The same happens with the molecules which move in the backward direction, so the molecules which cross this imaginary plane in the opposite direction. So here is the increment of the total x component of the momentum here. So when the molecule leaves that particular region in between the imaginary plane and the actual side wall, then again the momentum component changes by, okay, again the same mvx quantity, but this vx is for this particular molecule. But as we see, actually what happens in here, the vx is negative because the molecule moves in the opposite direction, so vx is negative. So the actual momentum of this particle is negative, but this particle after a certain amount of time leaves this imaginary space in between the imaginary plane and the actual side wall. So overall, the momentum has decreased by this amount. So I need to add the sign minus here in order to account for this phenomenon, that actually this particular molecule leaves this space. So I can say that this change is positive when Vx is positive, and it's negative mvx when Vx is negative. So this is the change of the momentum of all particles due to the molecules crossing this imaginary plane. Well, at the same time, there is some pressure force which leads to the collision. So the pressure force which is caused by the collisions of these molecules with the side wall. So overall, actually, due to these collisions, the momentum of the particle actually changes. And well, this produces the pressure force, and we can even say that in accordance to the momentum conservation law, we can say that the flow of the momentum through this imaginary plane should be equal to the pressure exerted by the gas onto this sidewall multiplied by the corresponding area of the sidewall. And since the flow of the momentum is the function which explains you how much the momentum changes per unit of time, then of course I don't need to multiply this by the amount of time which has been spent. So this flow of the momentum should be equal to the product of pressure multiplied by area. Okay, so now what we are left with, we need to determine the flow of that momentum, and in particular, to determine that flow, we need not only to understand the values of the momentum change as the certain particle crosses this imaginary plane, but also we need to understand how many molecules cross that imaginary plane per unit of time. So in our next few minutes, we are going to try to find out how many molecules cross this plane in both directions. So let's assume that, first of all, the most simple case, I would say that the case number 0, that all of the molecules actually have the same Vx component. And we know the number density of those molecules, n, and number density means the number of molecules divided by the volume, so number of molecules per unit of volume. So let's assume that we have a very specially designed situation in which the velocities of all of the molecules are equal to each other. So that's for the simplification purpose. And I think this solution would help us to understand what happens when actually the velocities of those molecules are different. So the number of molecules which crosses this plane per unit of time should be equal to the following. So if I want to find out the number of molecules which cross the imaginary plane per amount of time of delta t, I need to calculate, first of all, the volume of this imaginary cylinder, which has the base area A and the height of Vx delta t, since only the molecules which are located at a distance of Vx delta t from our imaginary plane would cross that imaginary plane in amount of time of delta t. So let me draw this with some different color in order to underline that the height of this cylinder should be equal to Vx delta t. So that means that the volume of that particular cylinder would be equal to the product of the base area A multiplied by Vx delta t. And that means that the number of molecules which happen to be in that particular cylinder would be equal to product of the number density, or sometimes which it is called the concentration, but I would like to say that the word concentration may have somewhat different meaning. For example, in chemistry, concentration means the let's say molar density of particles, and the concentration particularly applies to mixtures of some substances. So then it can be a mixture of gases or mixture of liquids. So in this context, I would like to use the number density in order to quantify the number of molecules which happen to reside in a unit of volume. So in order to find out the actual number of molecules which have crossed this imaginary plane, I multiply this delta V by n and get the following result. And finally, we can calculate the momentum flow. The momentum flow would be equal to n, okay, the number of molecules. I just rewrite the expression for the number of molecules which have crossed the imaginary plane during the amount of time of delta t, and I multiplied by the actual momentum carried by with each of these particles, which is m multiplied by Vx. And also I need to divide this by delta t, because I have said that this momentum flow is the amount of mechanical momentum carried through that imaginary plane per unit of time. That's why I need to divide it by delta t. And after I canceled out the delta t's, and also I can, let's leave this base area here. So I can write that this is n multiplied by m multiplied by Vx squared and multiplied by A. Okay, so this is it. This is it. And let's say we change the direction of Vx so that all the molecules not cross to that side, but they go to the left. In that way, the momentum carried by each particle would be minus mvx, but at the same time, the number of molecules which carry this momentum would decrease. So in that way, I can say that this delta n, the number of molecules which cross in this direction, would be negative. So I also need to add minus here, and these two minuses, as I multiply them, they would give me plus. So if I change the direction of the Vx, nothing would actually change in terms of the momentum flow. So the momentum flow by the particles which go in this direction and in the backward direction has the same value actually. Okay, so now we are going to make a next step and consider, so let's first leave this formula somewhere here, that this actual momentum flow should be equal to the product of pressure multiplied by the base area. And now let's make another step and consider the case number 1, in which all of the molecules have random values of Vx. So they have random values of Vx, which can be distributed according to some law of distribution. So instead of having the whole gas which has the same particular velocity Vx, we would have multiple components which have different Vx. So let's say that that Ni is the number density of those molecules whose projection of the velocity onto x-axis has values which are very close to some particular Vx. So let's say that in between some Vxi and Vxi plus dVx. And we also assume that this dVx is much smaller than Vxi. So we can do this, and let's say, since you should probably understand that as I close my interval, so as I take these Vx values smaller, dVx values smaller and smaller, the smaller number of particles actually has this sort of the velocity. So in order to reflect this fact, I would add this dNi in here in order to underline the fact that actually this is related not only to Vxi, but it's also related to dVx. And of course, the ratio of dNi over dVx is a probability density function for for the distribution of x component of the velocity. So it is some constant which depends only on Vxi but is independent of dVx. Okay, so I think this is not the most important part here. What is most important is that if we calculate the momentum flow, we need to calculate a sum of momentum flow corresponding to each of these d and I. So d and I is the, let's say, the component or the molecules of the gas which somewhat satisfy the case number 0, which we have previously considered. So in each of these d and I molecules per unit of volume, the x component of the velocity is almost the same. So I can write that the momentum flow in accordance to our previous solution should be equal to dNi multiplied by m multiplied by Vxi squared multiplied by the base area A. Okay. So if we take out the constant factors from this summation, which is m and a, we are left out with the following notation. And looking back here, well, I see there is a slight mistake here. I have said that this is the probability density function. I need to have some slight correction here. This is probability density function multiplied by the total number density of the molecules. So this is it. Of course, as I increase the density of molecules, the probability density function for Vx might not necessarily change. So as I have more molecules, I would have more molecules in each of my ensembles which contain molecules which move with the same velocity. So in here, I can write the following, that since this dNi is something which is proportional to dVx and also proportional to the number to the probability density function, and I can write that this is ma multiplied by the total number density n. And of course, since I have the summation over the infinite number of terms, this kind of a summation is actually an integral. So I replace the summation sign with an integral, and also I abolish these i's from indices from this expression. So I can write that this is actually rho of Vx multiplied by Vx squared multiplied by dVx. So this is the integral which comes from this summation. Okay, so now I need to do the final step and recognize in this integral the definition for the mean or average value or expectation value. So this is actually an expectation value for the Vx squared. If you look at this and compare this with the definition I have given during the previous lecture, this is exactly the expectation value of Vx squared. So I can replace this by the following, that this is base area multiplied by m by n multiplied by expectation value or mean value of Vx squared. This is how it looks like. And if I divide my momentum flow by the base area of the region which I consider, I would have the actual pressure. So after all of these steps, I was able to prove that actually the pressure of the gas is equal to n multiplied by m multiplied by Vx squared average. Now I need to do another step, and I may assume that, okay, this value is actually independent of the direction of x-axis, because the motion of gas molecules is chaotic. So they can move at any velocity at any direction, and these directions are completely random. So that means that if I, for example, choose another axis y, yeah, which is perpendicular to x, and the third axis z, which is perpendicular to axis x and y, then I can write that this Vx squared is equal to Vy squared average and equals to Vz squared average, and this comes from the symmetry. So that means that actually it doesn't matter where the axis is really directed, the expected value of the corresponding component of the velocity remains the same. So also I can combine all of them into the expectation value of speed, which is v squared, and according to the Cartesian, in the Cartesian representation, I can write that actually this v squared is equal to vx squared plus vy squared plus vz squared, and since we know that the average value of the sum equals to the average of each of these terms, I can write that this is vx squared average plus vy squared average plus vz squared average. And since three of them are completely the same, that should be equal to 3 vx squared average. Okay, so from this I can actually derive the x squared average and relate it to the average speed of the molecules. So the x squared average is 1 over 3 of the squared speed of the molecules. And I can insert it into this equation. So oftentimes you would see that the pressure is given by this formula, N multiplied by M multiplied by average v squared average. Okay, so I think that pretty much solved the initially formulated problem. So I can put some rectangle here to underline the importance of this formula, which connects the macroscopic property of the gas to its microscopic properties. And also we can slightly make a few steps for analysis of this equation. Let's say, for example, if you consider the average kinetic energy of the molecule, kinetic energy of a single molecule, it can be written as m v squared average over 2. And by this kinetic energy, I mean average kinetic energy of the translational motion. So this is average kinetic energy for the translational motion of molecules. By writing this, I again draw your attention to the fact that it includes only the translational motion of the molecules. Also, if I consider the kinetic energy, probably I should also include the rotational motion of molecules, which also has some kinetic energy in it. But here I neglect all of this rotational motion. So I only consider the translational motion. So this is the average kinetic energy for the translational motion of molecules. And from this, I get that the pressure equals to 2 over 3 multiplied by number density of the molecules multiplied by the average kinetic energy of the translational motion. Okay, so that's another curious fact that actually everything is related to the kinetic energy of the translational motion. Okay, the next part of our lecture would be devoted to the establishing the relationship between the thermodynamics and this kinetic theory. So in here I have pressure as a function of average kinetic energy of the translational motion. But I can also express the pressure via the ideal gas law. So let's continue on the next slide here. According to the ideal gas law, PV equals to nu RT, where nu is the amount of gas in moles. So I can actually write that this nu is the ratio between the actual number of molecules to the Avogadro number. And now I can write it as follows, that the pressure is N over V. So I take V to the right hand side and it goes directly to the why are they the same? I have a question. Valentina, please specify what you mean by they and the same. Probably some time has passed since the actual question. The same velocities. Okay, so you ask about the case number 0, which I have considered prior to the case number 1. So let me go back to the case number 0 here. Okay, the case number 0 in which I had all of the same velocities of the particles. I said that this is a preliminary problem which I consider in order to understand how this momentum flow can be determined if the velocities of all particles are the same. And next, after that, I made it to the second case, case number 1, and which is realistic one, in which the velocities are randomly distributed. So what I do here, and in the case y, the velocities are, it's about, okay, let's go to this slide. This Vx squared equals to Vy squared and equals to Vz squared. This is caused by the symmetry. So actually, in the case of gas, it doesn't even matter in which direction you move, because the gas properties are in some way rotationally symmetric, so it doesn't matter. So it doesn't make any kind of a direction somewhat more recognized by other directions. And that means that it doesn't matter in which direction I choose my initial axis. The motion of the gas particle should be rotationally symmetrical. So I mean that this random distribution of velocities should remain the same if I, for example, rotate my gas container by some degree. So in this way, it means that Vx squared equals to average of Vx squared equals to Vy squared and equals to average of Vz squared. Of course, if I consider each particle separately, each particle has its own direction and its own projection of the velocity. And if I calculate the projections onto different axes, and for each particle, these projections would be obviously different. But if I consider the whole gas as a very large number of particles which move randomly in different directions, then if I calculate averages of Vx, so if I first calculate all the x's and then calculate the average for the whole ensemble of gas molecules, then the quantities which I obtain would be the same since, for example, I don't have any external field which has, for example, some kind of a particular direction. So this is the usual assumption in the kinetic theory of gas, that I don't have any kind of a particularly distinguished direction in space. So in the case, for example, for the gas in this room where I am now in, the motion of molecules of gas is irrelevant to the direction. So, for example, I face in that direction and I experience the same amount of pressure of gas as if I, for example, move my face in that direction. So since I have the same pressure everywhere, and this coincides with the common sense, that means that actually this value of the x squared average should be independent of the direction of x-axis. So probably this explanation is somewhat better. If you look at this equation for the pressure, then it doesn't matter in which direction you measure that pressure, or how you rotate your sidewall plane of your container. So it would be all the same. Okay, so let's move on to the next one. Yeah. So in here, I try to establish the relationship between the equation for the pressure and the some basics of thermodynamics for the ideal gas. In here, I have the number of the amount of gas as n over Na. So that means that I should multiply this by R over Na and multiply it by temperature. Okay, this R over Na has a special notation, so it's usually called the Boltzmann constant. Boltzmann constant. And when we deal with kinetic theory, not with thermodynamics, this is much more popular than a universal gas constant. So in here I get that this is N multiplied by Kb multiplied by temperature. So if I compare this equation and the equation on the other half of the blackboard, which says that pressure is 2 over 3 multiplied by N multiplied by the average kinetic energy of the translational motion, from these two I can immediately obtain that average kinetic energy should be 3 over 2 multiplied by kBt. So that's the average kinetic energy for the translational motion. And from this we can actually obtain the molar heat capacity of single atomic gas. That famous formula that Cv equals to 3 over 2R. As you see, we already now have the same coefficient 3 over 2. So in the case of a single atomic gas, the internal energy is totally composed of kinetic energy of the translational motion of each molecule. So I can say that the internal energy is equal to the product of N multiplied by K. So in here I have 3 over 2 N times Kb times T, and from here I get that this is 3 over 2 times nu and Avogadro times Kb times T, and then I remember again that the product of Kb by the Avogadro number gives me the universal gas constant R, so that would give me 3 over 2 nu RT, and from here I get the common formula for the molar heat capacity of the single atomic gas at the constant volume. Of course, this formula is invalid for diatomic and triatomic gases, because in our calculation of the internal energy, I have assumed that only the translational motion of molecules contributes to the internal energy. But in the case of gases which have more atoms in one molecule, there are also other contributions, like the contribution from the rotational kinetic energy, the kinetic energy of the rotational motion. But nonetheless, this can be considered as the kinetic derivation for this heat capacitance of molar heat capacity of the single atomic gas. Let's now continue with the Maxwell distribution. During this lecture, I would give you a derivation of the Maxwell distribution in the way which was ascribed to James Clerk Maxwell himself. So it is said that exactly this approach was the one which Maxwell used in his famous derivation. This approach allows to obtain Maxwell distribution in a more simple manner than the mathematically rigorous approach. So I would use this approach during the lecture, but I will also give you a link to the approach which is more rigorous than this one. Okay, so the aim of our aim is to determine the distribution for velocities which have, of course, 3 Cartesian components, and I need to have this probability distribution function, and this probability distribution functions give me the element of probability that my particular molecule has some velocity v given by some vector, I mean by the 3 numbers, and also, of course, the velocity cannot exactly coincide with this value because it's a continuous random variable. So I need to give also some to allow some deviations from this value of dvx, dvy, dvz. So this means that the velocity is located in between. So vx is in between vx and vx plus dvx. Vy is in between some vy to vy plus dvy. And the same for the vz, that we have vz in between vz plus dvz. So if you draw this in the so-called velocity space, so the space in which coordinates are vx, vy, and vz, then this would correspond to some element of volume in this velocity space, dvx, dvy, dvz. So I need to calculate the probability that my particle would have the velocity which falls into this small cubic or parallelepiped space in my velocity space. Okay, so this should be the answer. But of course, we should have some more assumptions to determine this rho of v. And the first assumption follows from the rotational symmetry of this problem, that non-direction is particularly distinguished with respect to other directions. So that means that if I change the direction of that velocity v and consider 2 different velocities v1 and v2 which have different directions but have the same absolute value, then we should expect that this probability density would not change. So that means that the probability density as the function of velocity should be actually the function of speed, the absolute value of velocity. So first, I have that rho of v equals to actually some function of speed, so v without vector. And the second assumption which we are going to use is much less trivial. This is much less trivial. But nonetheless, it was the one which was used. And the second assumption says that the motion of particles in x, y, and z direction is independent. So that means that actually my probability density function is equal to the product of 3 functions, phi of vx, phi of vy, and phi of Vz. So that corresponds to the mathematical expression of independence. So that means that for example, it's a very non-trivial assumption. It says that, for example, let me consider two particles. And for the first particle, we know that the x of this particle is very small. And for the other particle, we know that the x of this particle is large. So now I'm going to ask you, like, for example, what would be the y component of each of these particles? So what would be the y velocity component of these particles? So for example, I would expect that on average, the component of velocity of the first particle in y direction would be greater than the component velocity of the second particle in y direction. But this assumption says the opposite. It says that the distribution of the y component of the velocity is actually independent of the x component of velocity. So if I have large x component of velocity, it doesn't change the distribution of y and z components of velocity. So this is a really non-trivial assumption, but it really works. And this assumption is taken without any, of course, any derivation. So it's like an axiom that we should take this as some established fact. Well, so, and this allows us to determine that actually this rho of v and phi of vx, vy, and vz are in some very close connection. And not every function phi would produce you a probability distribution which depends only on speed. Let me show it. On the second slide here. And let's consider this only in 2 dimensions for simplicity, because the arguments are exactly the same, whatever the number of direction is actually here. So let's assume that phi of Vx is some uniform function which is constant if the absolute value of Vx is less than some critical velocity, and 0 for any Vx which exceed the critical velocity. So I can write that if I can plot this function as follows. So in here I have V critical, in here I have minus V critical, and in here I have this constant. So that gives me the following function of phi. And if I calculate the product of phi of Vx times the same phi for Vy, that would say to me that I have this square, and the side of this square is equal to double the critical velocity Vc. And inside this square, my probability density equals to c squared, while outside the square it is 0. But if I want to look whether this probability distribution has this property of independence of the velocity direction, that of course is wrong. For example, if I take velocity which goes here and rotate it slightly, that the end point of this vector happens to come outside of that square, then I would have 2 different vectors. Here V1 and V2, which have the same absolute value. So these endpoints of these 2 vectors are located on some circle of a certain radius. but the probability density corresponding to V1 is c squared, while the probability density at V2 is 0. So this probability density function doesn't satisfy the condition number 2, which I have written on the left side of the blackboard. So not every function satisfies the second assumption. So let's go back here. Not every function satisfies this assumption. So this assumption in a certain way is a very strong assumption, which gives you a very stringent restriction onto the probability density functions. Okay, I would like to comment the fact that actually this function phi of the x, vy, and vz is the same. This actual function is the same. If it's not the same, that would violate, again, that would violate the equivalence of directions. So that would say that, for example, let's say that phi x for phi x and phi y and phi z, let's say they are different functions. So that means that for some reason x-axis has different rights with respect to y and z axis. No, it's not the case. So since all the directions in space are equivalent to each other, then we need also to require that all of these three functions actually are exactly the same function. It's just that I use different numbers or different arguments for the same function in order to calculate the final result. Okay, so now based only on these two assumptions, let's try to understand what functions phi and rho can satisfy these two conditions. So let's go on this blackboard. Okay, so let's assume, let's consider two vectors, v1 and v2, which are approximately equal to each other. Approximately equal. So there is only a very small difference between these two vectors. And I want to determine, based on the second relation, that rho of v equals to phi of v1x phi times v1y phi times v1z, and also according to the property number 1, that rho of v1 should be equal to rho of v2. So they are slightly different, but they have exactly the same absolute value. So that's what I mean. So I move in the velocity space on the circle, which has the center on origin. So I slightly change the direction of vector v while preserving its absolute value constant. So that means that since these two functions, rho of v2 and rho of v1, are exactly equal, so that means that I can write the following identity. Also, let's assume that v1z exactly equals to v2z. So let's consider only rotations of the velocity vector in xy plane. That would allow us for a slightly more simple derivation. So I can immediately cancel out these two from this equation. And now I have these two products which are exactly the same. So to simplify further calculations, let me calculate the logarithm of both sides of this equation. So that would give me the natural log of phi of v1x plus natural log of phi of v1y exactly equals to natural log of phi of v2x plus natural log of phi of v2y. And let's assume that the function f of v, which equals to exactly the natural log of phi of v of the same argument, so that this expression can be written somewhat more simply. So that says f of v1x plus f of v1y equals to f of v2x plus f of v2y. So this is just simply the algebraic expression. So what we are doing now actually is that we are solving some functional equation. So in here I have some properties onto which this function should satisfy, and I try to figure out what kind of functions I may put in here in order to satisfy these properties. Okay, so let's assume now that the function f has the derivative. So if I slightly change v1x and v1y, what I actually get is that, okay, that df of vx plus df of vy should be 0. So the small changes, so if I calculate the difference of if f of v2 minus f of v1 of x, f of v2y minus f of v1y, so that means if I bring these two terms to the right hand side of this equation, what I actually have is the change of df of vx and df of vy. Okay, so let's say at the point number 1. So this is the initial point, and this is the final point. And I can write that actually these changes, so these increments to the function, are equal to f prime, that is the derivative of the function, multiplied by dvx plus f prime of vy multiplied by dvy. And that should be 0. And of course, my changes dvx and dvy are not arbitrary. These changes are restricted in such a way that v1 should be equal to v2. So in particular, that means that v1x squared plus v2x squared equals to v2x squared plus v2y squared. Oops, v1 x squared plus v1 y squared equals to v2 x squared plus v2 y squared. So that means that I can write that 2 multiplied by v1 x dvx plus 2y v1y dvy is 0. So the changes of dvx and dvy should be connected linearly to each other in order to preserve the absolute value of the velocity. Well, I can even say that if I consider very small changes, then if I move around in this circle, that means that my change dv should be perpendicular to the initial velocity. And this is exactly what this equation says. So this is a scalar product of the vector v1x, v1y multiplied by the vector dv, which has components dvx and dvy. So if I take out these coefficients too, so this is exactly the scalar product of these two, and it says that, yeah, dv is perpendicular to v1 if I consider very small changes. So this is the meaning of this equation. So now I plug it into into this. So I can derive dvy from this equation and plug it into this equation with derivatives, which brings me to the following, that f prime of v1x multiplied by dvx plus f prime of v1y multiplied by dvy, but dvy itself is minus dvx times v1x over v1y, and this is 0. And now I cancel out dvx, and now I should try to write it in the form which separates variables v1x and v1y. So I can write it like f prime of v1x over v1x equals to f prime of v1y over v1y. As since initially we didn't have any kind of restrictions of v1x and v1y, so that this equation should be valid for any v1x and v1y I choose in my in my consideration. So that means that actually what this means is that f prime of v over v should be constant. That should be constant. So now let's solve this equation. So I have here a simple differential equation that, okay, I can even write it f prime of v, so the derivative of some function, is equal to cv. So this is a linear function of velocity, which what kind of function should there be? So what kind of function, its derivative is the linear function? Of course, it's quadratic function. So I can write that f of v is another constant a, because the change of this constant doesn't change in any way like the derivative, plus cv squared over 2. cv squared over 2. So this is f of v, and now we go back to this function phi. We remember that f of v is actually the logarithm of phi of v. So that means that phi of v, if I go backwards, if I want to derive this from this, that means that I need to calculate the exponent of f of v. So now let's go back in here. That means that f of v is the exponent a plus cv squared over 2. Or I can write that I can take exponents of a as some constant. So I can write that this is some constant a multiplied by exponent of cv squared over 2. Of course, this over 2 doesn't matter because I derive some arbitrary constant by the factor of 2. Well, let's leave it like this. And probably let's add a minus here. Minus here. Again, it corresponds to the multiplication of the constant by number -1. So the constant remains a constant if I do this, but it's more convenient because in this way this constant c would be positive if I have minus here. That's a very small minus. Okay, it can't be seen probably. Let me fix it. So in a mathematical sense, of course, there is no such equality between exponent of a plus cv squared over 2 equals to a exponent minus cv squared over 2. So that's algebraically wrong. But what I imply here that actually I can redefine this constant in any way you want it. So I assume that instead of a, I take that this is a new a, which is exponent of a, and here I have new constant c, which is the previous constant c multiplied by -1. So in this way, it doesn't matter. I can redefine this constant. I can, since they are constants, I can add another constant, and it will remain a constant. And I can also multiply it by any other constant, and it will remain a constant. And of course, I can calculate the exponent of the constant, and it will again be the constant. So this is the general case of a, and okay, for the f of phi of v. And in here I have minus for the simplicity, because if I bring my velocity v to the infinity, so if I consider very high velocities or very high speeds, of course, at any given temperature, the fraction of molecule which has a very large speed is very small, and it gets smaller and smaller as you increase that particular speed. If I have plus here and my constant c is positive, then my distribution is wrong in such a way that first of all it cannot be normalized, and secondly it predicts that almost all molecules have kind of infinite speed. So as you increase this speed, then the probability density would also increase. So that's wrong in a physical sense. So of course, mathematically, this kind of distribution would satisfy my initial two conditions, but we should always remember that what we are doing here is slightly more than mathematics. We are trying to describe some physical system using the mathematical approach. So of course, we should be in some relationship with reality. So in that way, that means that this constant c would be positive, and or the initial constant c would be negative. Okay, now as we have determined this phi of v, we can try to figure out what these coefficients a and c are, and how they depend on the physical conditions of our gas. Okay, so let's consider the probability distribution function phi of vx. First of all, it should satisfy the normalization condition. If you have forgotten for some reason what normalization condition is, then you should probably check the previous lecture where I have said something about it. But the normalization condition is as follows, that phi of vx integrated over all vx from -infinity to +infinity should be 1. That is the fact that each molecule has some x components of velocity. So that means that the probability of for the particle to have some component of velocity in between -infinity to +infinity should be exactly 1. So that's what normalization condition says. And okay, so that would give us the following: that integral -infinity to +infinity of a times exponent minus c vx squared over 2 times dvx should be 1. Okay, now I want to ask you a question whether you have calculated anywhere the integral of this type. Please write somewhere in chat if you had some relationship with these integrals before or not. That would also allow me to understand how many people actually listening to this lecture. Improper integrals, okay, but this particular improper integral of exponent and something is squared inside this exponent. So usually, if you integrate the exponent, it's something linear inside the exponent, like exponent of -2x dx. That is very easy to be calculated. But if I have minus vx squared in here, have you done this before? Okay. Well, okay, let's assume that you haven't done anything with these kinds of integrals, so I want to calculate this integral during this lecture. So it involves, I think, but it's not a common exercise. So yeah, well, I can agree with this. So probably I just asking whether you had to do with these integrals during the mathematics courses in our university. If you haven't done so, then I can calculate it now. Okay, so I'm going to calculate it. So the calculation of this integral involves a very interesting trick. So let's assume that, okay, from this equation I can say that a is 1 over the integral of exponent of minus cvx squared over 2 times dvx. Yeah, so this exactly goes, if I take this constant a out of this integral, and then I divide both sides of the equation by this integral, I get exactly this answer. So I need to calculate this integral, and let's assume that this integral equals to capital I. I just introduce a new variable here, exponent of minus cvx squared over 2 times dvx. Oh, this is capital I. So I go from minus infinity to plus infinity. So of course I have no idea how to calculate it when I live in this one dimension, because none of the functions I know has this type of a derivative. So I cannot calculate this integral using the very same approach as we typically use for calculation of these type of integrals. I need to do some transformation. And let's do this transformation by making this integral two-dimensional. So this I is equal to this, but of course the integration variable can be taken in any way I want. So I can, for example, say that the same integral I equals to the minus integral from minus infinity to plus infinity of the exponent minus cvy squared over 2 times dvy. Because it's exactly the same integral. I just have renamed the integration variable from vx to vy. So far nothing interesting goes here. Now we go to the next slide. I want to calculate I squared. So I take the product of two i's on the right hand slide. So I write like follows. The exponent of minus cvx squared over 2 dvx, that's the factor number 1, multiplied by the integral of the exponent of minus cvy squared over 2 times dvy. Oops. And this can be considered as a two-dimensional integral. Two-dimensional integral from minus infinity to plus infinity, from minus infinity to plus infinity. Because with respect to the integration over dvy, all of this, which is written here, is a function of the x. So this can be considered a constant with respect to this integral. So I can take this and treating it as a constant, bring it under the integration of dvy. So that would give me the following, that I have exponent of minus cvx squared over 2 minus cvy squared over 2. That's how product of two exponents can be transformed. And again, multiplied by the product of dvx, dvy. So integration over two variables here. So if I look at this, it looks like as if I have some sort of a function which is determined in a two-dimensional space, x and y, and it's integrated over the whole space. Okay, and for this kind of a function, I can write that this is integral over R2. This is two-dimensional real plane, and integration is performed over the function minus cv squared over 2, and it's integrated over dvx, dvy, where v is the speed. And speed, of course, is determined as v squared equals to vx squared plus vy squared. So that's how I determine the speed. And now I am going to calculate this integral by transforming this to the polar coordinates. In the polar coordinates, the coordinate of each point is determined by the distance from the origin, and since I integrate in Vx, Vy space, so the distance from the origin is actually the speed, v, and is determined by this angle phi. So I can say that I divide my two-dimensional plane into these circular rims of some very small thickness and integrate it by calculating the sum of this value over these rims. So I can write that this is actually the element of area, dA, and when I divide my two-dimensional space in these circular rims, I can write that the element of area is given by the length of the circle itself multiplied by this thickness dV. The thickness of the circular rim dV. So I can write that this is 2 times pi times v multiplied by dV. So in here, when I write the element area in this form, my integral is no longer two-dimensional. So it becomes a one-dimensional integral, which is defined for velocities from 0 to infinity. So if I want to cover all of this space, that means that my v changes from 0 to infinity, not from minus infinity, but now from 0. And I have the integration of the exponents of minus cv squared over 2 multiplied by 2 pi v dv. Okay, so far it looks like an integral of the one-dimensional function. Now let's continue to the second slide. So I can write that I squared is the integral from 0 to infinity of exponents of minus cv squared over 2 multiplied by 2 pi v dv. And as you see, actually this v dv here can perfectly give you why the boundary is 0. Okay, let's go back here. So in my transformation, when I go from Vx and Vy to the actual speed v, and then I go to my, so I take the integral over this whole two-dimensional space. But for each point in this two-dimensional space, the quantity which I call v changes from 0, that's the origin, and to infinity, that's for the faraway points. So none of the points in two-dimensional space can have the speed which is negative. So that's why I start my integration from 0, or I can say that actually my division of the two-dimensional plane into these circular rims starts with a small circle around the origin and continues further in this manner. So in this way, when I do this kind of a division of the plane into the elements, the smallest velocity possible, the smallest speed possible here is 0. So that's why my integration starts with 0, not with the minus infinity. Okay. So let's assume like this is the fact that if I change the integration from Vx and Vy, then to this speed v, then I should start my integration from 0 speed, because for any molecule, okay, for any velocity involved here. The speed actually is some quantity in between 0 and infinity. Okay, so now we get back here, and I think it's very convenient here to integrate in terms of variable which is v squared. So for this we need to collect this v dv into something related to v squared. So I do it like this. Multiplied by pi times dv squared. Okay, so now it's no longer an integration from over v, but the integration over v squared. And what's important here is that this is the very type of integral which you are able to calculate, because the integration variable v squared is now linear in the exponent. So the integration is linear with respect to the v squared. So if I, for example, calculate exponent of minus cv squared over 2d exponent over dv squared, I would get minus c over 2 multiplied by the same exponent, cv squared over 2. So I can write that from this, that minus 2 over c times d of exponent minus cv squared over 2 equals to the exp of minus cv squared over 2 times dv squared. So this is exactly the same as the under integration with the exception of this constant pi, which can be taken out actually. So after I do this, I can write that the final answer is minus 2 pi over c times exponent of minus cv squared over 2 calculated at the infinite point minus the same quantity calculated at the 0 point. So if I assume that v squared is infinite and insert into this expression, then it would give me that exponent of minus infinite power is actually 0. So it's like, say, e to the minus infinity. This is 1 over e to the infinite power. And of course, as you increase this exponent, the exponential function grows infinitely. So the limit of e to the minus x as x goes to infinity is 0. So that means that at the upper boundary I have 0. At the lower boundary, this exponent gives me 1. So finally, after I use these facts, I would get that the integral equals to 2 pi over c. Exactly. Because the calculation at 0 point contributes to the total value of the integral with the coefficient minus 1, and minus 1 times minus here would give you plus 1, so that would give you 2 pi over c. So this integral is I squared is 2 pi over c. So that means that since this is I squared, now I can calculate I itself. I is the square root of 2 pi over c. Now we go back to the to this method and check whether it is possible to calculate, for example, the integral of exponent of minus cv squared over 2 times dv in some finite boundaries from a and b. So previously we have calculated this in for the improper integral in infinite boundaries, but if I have boundaries from a to b, how it would work? This method would not allow us to calculate this integral within finite boundaries. And the reason is follows. And if I, for some reason, attempt to do the same trick with transition to two dimensions, Vx and Vy, and try to calculate it in finite boundary from A to B, so if I do the same multiplication trick as I have done previously, that means that I need to calculate the whole integral over this square. So the same trick as I have used, which involves the transition from Cartesian to polar coordinates, would not work anymore, because the region of my integration is not invariant with respect to this transformation. Because if I like try to calculate it in circular reams, that would mean that my different circular reams would have slightly different range of angles in here. So the whole construction will collapse, and I would not be able to calculate the definite or proper integral in the same manner. And as it turns out, actually this integral cannot be calculated in elementary functions, and there is a special function which is related to this integral, which is called error function. I don't remember, it's probably defined like something like this. Integral from 0 to x, exponent of minus, let's say, some y squared over 2 times dy. So y changes from 0 to x, so that would give you like, probably from minus x to x. I don't actually remember the details about the definition of error function, but this kind of function is cannot be determined in elementary functions. So it cannot be expressed through exponents, trigonometric functions, and this any exponential series. So this is the function which is not expressible in elementary functions. But nonetheless, the improper integral can be calculated nicely. And let's write somewhere the main result in here. That an integral of exponent of minus cv squared over 2 dv is equal to square root of 2 pi over c. Okay. That's the result of our calculation from minus infinity to plus infinity in here. Okay, so that would allow us to determine the normalization constant, since, as I have already said, on the right hand of the blackboard, it says that normalization constant for the distribution is given by 1 over this integral, which gives me c over square root of 2 pi. So that means that f of phi of vx, for example, is square root of c over 2 pi multiplied by exponent of minus c vx squared over 2. Okay, so that's for the one-dimensional distribution of velocities. If I am interested in the three-dimensional probability density function, that means that I need to multiply phi of vx times phi of vy times phi of vz, and that gives me c over 2 pi to the power of, let's say, 3 over 2. Since each of them is to the power of 1 over 2, then if I multiply them 3 times over, that would give me a c over 2 pi to the 3 over 2, multiplied by exponent of minus c v squared over 2. Exactly what's what is demanded by this function rho. This function rho says that it should be only the function of the speed, and this is exactly the case for this particular distribution. Okay, so now let's determine the constant c. Let's determine the constant c. And the only way to determine the constant c is to relate it to, for example, some of the known values. And one of the known values, which we have determined previously, is the average kinetic energy of the translational motion, which is 3/2 kBt. Or if I look at the kinetic energy in some particular direction, mvx²/2, that would give me kBt/2. So overall, I can say that average of Vx² is equal to kBt/m. So that's what I have. So this condition is going to be the equation for the constant c. Okay, let's calculate this Vx² average. By definition, the expected value of Vx² should be equal to phi of Vx multiplied by Vx² times dVx. So that gives square root of c/2 pi multiplied by exponent of minus cVx²/2 multiplied by Vx² multiplied by dVx. Okay, so now we have another kind of a nasty integral which requires some tricks for its calculation. And okay, let's do the calculation as follows. And let's probably try to figure out how this integral should be calculated, not only when Vx is in the power of 2, but for any power. So this is the integral from -infinity to +infinity. Well, you know that if I take, for example, the odd power of Vx, then that would give me an odd function, and the integral of the odd function over the symmetric interval would give you 0. So in order to bring some sense into it, I'm going to write that this integral is actually equal twice the integral from 0 to infinity of square root of c/2 pi multiplied by exponent minus cVx²/2 multiplied by Vx. Okay, let's say now not to the power of 2, but to some arbitrary power n, to the power of n, multiplied by dVx. And of course, this integral would be positive for any value of n. It doesn't matter whether n is even or odd, and for some reason it might be a good idea to have it calculated for both even and odd values. And next, let's take out this constant out of the integral. So that would give me 2c/pi multiplied by the constant from integral from 0 to infinity of exponent minus cVx²/2 multiplied by Vx to the n dVx. Okay, so far we have the value of this integral for n which equals to 0. For n which equals to 0, it's given by this expression, but it's given by this expression, but as you see, it goes from -infinity to +infinity. So in order to conform to the form on the right part of the blackboard, I'm going to write it as follows: that integral from 0 to infinity of the exponent of minus cv²/2 multiplied by dv equals to pi over 2c. So I just divide both sides of this expression by 2, so to get this answer. And also for simplicity, let's introduce some sort of a function, for example, capital F of n, to represent the integral from 0 to infinity of exponent of minus cv squared over 2 multiplied by v to the n multiplied by dv. So the knowledge of this integral would slightly simplify the solution of all problems related to Maxwell and Boltzmann distributions, not only Maxwell distribution, but Boltzmann distribution too. So we need to understand how to calculate these values. And so far what we have is f of 0 is equal to pi over 2c. It's also quite easy to calculate this integral in the case when n equals to 1. Let's go here, n equals to 1, because it pretty much corresponds to what we have done like with two-dimensional integration. So if I write n equals to 1, then f of 1 is the integral from 0 to infinity exponent of minus cv squared over 2 times v times dv. Like when we have calculated for n equal to 0, we had here 2 pi v dv. So now we don't even have this 2 pi, but I can write it as from 0 to infinity exponent of minus cv squared over 2 times dv squared over 2. So now this integral is a simple exponential integration over v squared over 2. So the result is 1 over c. I'm not going to repeat all of this stuff again, but well, you can check for yourself. Like for example, let's say x is equal to v squared over 2, some additional variable. So now the integral from minus infinity to infinity of exponent of minus cx dx should be calculated. And if you calculate it, it will give you exactly 1 over c. Okay, so f of 1 is also easily determined. But how should we determine f for other integer quantities of n? So that's the recipe for any f of n. If I have f of n from 0 to infinity, x minus cv squared over 2 times v to the n times dv, there is a very good way to calculate integrals. It's called to integrate by parts. So we need to integrate this by parts. And the main rule for this calculation of integrals is as follows: that if we have integral of the function a over some db, then this integral is equal to ab minus integral of b over dA. Okay, so far it doesn't look like a very useful equation, but this is typically used when we try to calculate integrals which contain the product of different functions. So let's say I want to calculate the integral of a g dx, and I understand how to calculate the integral g dx. I understand how to do this. So that is why this is called the integration by parts. I can do only part of this integration. So g dx, I know like there is some function capital G whose derivative capital G gives me small g. So that means that this can be written as f times dg. Now I apply this rule, and this rule exactly follows from the multiplication rule for differentiation. So this is the consequence. So like the derivative of a b function is a times db plus b times dA. So this is how this integration rule works. So now I calculate f times dg, so that would give me f times capital G minus integral, and now I do the following. So I have here g multiplied by dA, okay, multiplied by df. So this is f times capital G minus integral of g times f prime times dx. So that's what actually happens. So if I can calculate the integral g dx, then I can slightly transform my integral into this form. So this is actually the recipe, and we are going to apply this recipe in such a way that the exponent here decreases after we apply it. So how it will work here? So let's say we have f of n equal to integral from 0 to infinity x minus cv squared over 2 times v to the n times dv. And we can actually calculate the part of this integral which corresponds to f of 1. So we know that exp of minus cv squared over 2 times v times dv is actually minus 1 over 2c d exp of minus cv squared over 2. Or not? Or it's just 1 over c. 1 over c multiplied by this. So if I calculate the derivative over v, that will give me this exponent first, and then the derivative of the exponent here. So that would give me minus c over 2, which eliminates this. And then I take the derivative of v squared, that will give me 2v. So, okay, so that would give me this exactly. So that means that I can take that small function g is actually exp minus cv squared over 2 multiplied by v, while capital G is equal to minus 1 over c times exp minus cv squared over 2. And then apply this rule. So that means that what I have here as a function f is v to the power of n minus 1. V to the power of n minus 1. So now I'm going to apply it. That gives me minus 1 over c exp minus cv squared over 2 times v multiplied by f, so multiplied by this goes multiplied by v to the n minus 1. So altogether that gives me v to the n minus 1. So I take capital G multiplied by f. So this is the first part, which should be calculated from 0 to infinity. And actually you can check it, but all of this is actually 0. All of this is 0 because if n is greater than 1. So for n equal to 1, we already know how to calculate it. So what we are interested in, if we have n which is greater than 1, if I just plug v equal to 0 into this expression at n which is greater than 1, that would give me 1 for the exponent and 0 for the v to the n minus 1. So altogether that would give me 0. At the infinite point, the exponent decreases faster than any exponential function than here. So that means that at the infinite point, that would give me 0, 2. So altogether 0 minus 0 for the integration. So we apply again that partial integration rule. So the first part would be 0, and I should also to calculate here. The second part is integral of minus 1 over c multiplied by f prime. F prime would of course give me n minus 1 multiplied by v to the n minus 2. So here goes capital G multiplied by n minus 1, v to the n minus 2, dv. And if I take all of the constants out of this, integration is again from 0 to infinity. So if I take all of the constants out of this, I would get, okay, let's continue on the next slide. I would get that f of n is equal to plus n minus 1 over c integral from 0 to infinity of x minus cv squared over 2 multiplied by v to the n minus 2 multiplied by dv. If I look at this expression, all of this is actually exactly the same integral, but for n equal to n minus 2. So I can write that f of n is equal to n minus 1 over c multiplied by f of n minus 2. So now I have a kind of a formula which allows me to reduce the integral for higher values to the integrals which have lower values of n. And I know f of 0, which is again pi over 2c, as far as I remember. And I have f of 1, which is 1 over c. So now I can determine f for any integer value. Like, for example, f of 2 should be 2 minus 1 over c multiplied by f of 0. Okay, so that gives me 1 over c square root of pi over 2c. Good, that works. F of 3 is 3 minus 2 over c multiplied by 1 over c, or 3 minus 1 over c multiplied by 1 over c. That gives me 2 over c squared. And we can continue to any value of n. Okay, so now let's get back to the initial problem. So where I have started this from? I have started this from calculation of x squared average. So that means that in here, the x squared average is equal to square root of c over 2 pi multiplied by f of 2. Now I look at this. This is c over 2 pi multiplied by 1 over c multiplied by square root of pi over 2c. So that gives me 1 over 2c. That's the x squared. Okay, so this is the x squared average, 1 over 2c. So in the end, we also know that mvx squared average over 2 is equal to kbt over 2. So that means that the x squared average should be equal to kbt over m. And that is exactly 1 over 2c, and there is some mistake there probably. Like, I kind of feel that there should be some sort of a mistake. Probably not. Let's see further. So that means that c equals to kbt over c equals to, okay, C equals to m over 2 kBt. Okay, that's slightly different from what I have expected, so let's see where we have done a mistake. Okay, let's go back here, and let's start from here. Well, I understand now. So in here, I have forgotten about this coefficient too. So all of the integrals were calculated correctly, but in here, actually, I need to multiply this by twice the f of 2. So that would give me coefficient to here, coefficient to here. So that would give me exactly 1 over c. So now I have c equal to m over kBt. So that finally allows me to write the Maxwell distribution for the velocity components as follows. That is square root of m over 2 pi kBt multiplied by exponent of minus m vx squared over 2 kBt. Okay, so that's the Maxwell distribution with all of the coefficients and relationship with thermodynamics, with the temperature. If you look at this, you would see that actually that in the exponent, what I have is actually the energy of the translational motion in the x-axis divided by kBt. That's a good thing to notice. So please note it somewhere, because the box, for example, Boltzmann distribution would look quite the same, but instead of kinetic energy, we would have potential energy. So all of these distributions, they have kind of similar structure. I have some energy divided by kBt, which I can call like thermal energy. So kBt is some thermal scale of energy. If I multiply temperature by the Boltzmann constant, that would give me exactly energy in joules. And I divide the actual energy by this thermal energy kBt, and that would give me like this exponent here. And there is a normalization constant. Okay, so what we are left with, so we know like the Maxwell distribution for the velocity components. Now the total Maxwell distribution is like this. Rho of v should be m over 2 pi kBt to the 3 over 2 multiplied by the exponent of minus mv squared over 2 kBt. So the kinetic energy of the molecule divided by kBt. Also, among the useful facts that I have derived, so I'm going to collect everything in one page, are these equations for the integrals. So f of n determined as the integral from 0 to infinity of x minus cv squared over 2 dv is, so now the different cases, square root of pi over 2c, that's for n equal to 0, then 1 over c, that's for n equal to 1, and n minus 1 times, n minus 1 over c times f of n minus 2 for any n which is greater than 1. Okay, let me check again once again. So f of 1 is 1 over c, f of 0 is pi over 2c, so now everything looks like correctly. Also, in the course of our calculations, we have established that Vx squared average is equal to kbt over m, or once again, this is kbt over n, which is 1 over c, which is 1 over c. This is the x squared. And next, from this I can determine the average squared speed of the particles. The average squared speed would be sum of the x squared average plus Vy squared average plus Vz squared average. That is 3 kbt over m. That's another one. Average kinetic energy is given by 3 over 2 kbt. That's kinetic energy for the translational motion. Now let's calculate some more variables. So let's say I'm going to collect everything here, so I'm going to do the calculation on the left side. So the next one I'm going to calculate is the average speed. Since speed is always positive, then average speed should have some positive value. So let's calculate it. By definition, the average speed is the integral of rho of v it's slightly more difficult. So we are slightly preliminary to go to this. To calculate the average speed, we first of all should derive the distribution for speeds. So far we have the distribution for velocities, and there is a huge difference between two of them. So it says that the distribution for velocity, that the probability for the particle to have a certain velocity is equal to rho of v times dvx, dvy, dvz, where rho of v is given by m over 2 pi kb t to the 3 over 2 multiplied by exponent of minus mv squared over 2 kbt multiplied dvx, dvy, dvz. A Maxwell distribution in this form is not convenient for calculation of the average speed. So we need to formulate to calculate the probability that the velocity of the particle is in, not the velocity, but the speed of the particle is in between v to v plus dv. And we can do this from Maxwell distribution. So if we look at the region in velocity space, which is occupied by all of the molecules which have the speed in between v plus to v plus dv, that is the region in between two spheres. One of the spheres has the radius v, while the other sphere, so it is a sphere, so I draw the cross sections of this sphere with all three coordinate planes, and I need to calculate actually the probability for the particle to be in a small spherical layer which has radius of v and the thickness of dv. The volume of such layer, dv, is equal to 4 pi v squared, which is the surface area of the sphere, multiplied by the thickness, which is dv. So we can write that in here, actually, I have, this is actually the element of volume in the velocity space. And here the distribution is independent of the direction of the velocity, so that means that the probability that the particle has the velocity, the speed in between v to v plus dv is actually m over 2 pi kbt of 3 over 2 multiplied by exponent of minus mv squared over 2 kbt. That remains the same, but there is another stuff which comes from the element of volume. So instead of dvx, dvy, dvz, we would have an additional coefficient of 4 pi v squared and then multiplied by dv. So that means that this new function, which contains this 4 pi v squared, gives us the probability density for the distribution of speeds. So please notice that we have slight changes to the original Maxwell distribution when we go from velocities to speeds. So we have an additional factor there. And this is something which can be expected when you change the quantity onto which you calculate with respect to which you calculate the probability density. Because if in the when you change the quantity, then you also change the configuration of that quantity's space. So the elementary volume in the velocity space changes to something slightly different in terms of speed space. So now I have this distribution for velocity, for speeds. So now I'm ready to calculate the average speed. So the average speed is given as, okay, I take m over 2 pi kbt times 3 over 2 multiplied by, okay, so for the calculation of average speed, I need to multiply the probability density function by the speed itself and integrate it. So I also take 4 pi out of the integral. I also take 4 pi. So what is left here is the integral from 0 to infinity of x minus mv squared over 2 kbt multiplied by v cubed times dv. So this is actually f of 3. So I have the third power in the velocity here. So this is f of 3. So that means that now I need to go to the next blackboard for calculation. So let me rewrite it. The average is m over 2 pi kbt to the 3 over 2 multiplied by 4 pi multiplied by f of 3. So let me see it once again here. Multiplied by 4 pi multiplied by f of 3. Good. And f of 3 is 2 over c multiplied by f of 1. 2 over c multiplied. And f of 1 is 1 over c, so this is 2 over c squared. 2 over c squared. And since c is equal to m over kbt, then I can write that this is 2 kbt squared over m squared. So that's f of 3 for Maxwell distribution. So now I insert it in here, and I get that, okay, I can write like follows. 4 pi over 2 pi to the 3 over 2 multiplied by m over kbt, which is actually the c, m over kbt to the 3 over 2 multiplied by 2 multiplied by kbt over m to the power of 2. And as we see, actually, these two, m over kbt and kbt over m, are actually the flipped over ratios. So I can use that this is 8 pi over 2 pi to the 3 over 2 multiplied by kb t over m to the power of 1 over 2. So altogether that gives me square root of 8 kb t over okay, is it correct? So 8 over 2 to the power of 3 over 2. So this is 8 over square root of 8. So that leaves me square root of 8. Pi over pi to the power of 3 over 2 gives me 1 over square root of pi. So that's the answer. And that's the final equation for the average speed of molecules, 8 kBt over pi m. And of course, in practical applications, so in here, this equation is written in variables which are relative to the single particle. So I have mass of a single molecule here. I have Boltzmann constant. But of course, when you do the calculations in problems, it is not convenient to always calculate the mass of a single molecule. So I just need to multiply both parts of this fraction by Avogadro number, so that would give me 8RT over pi mu, where mu is the molar mass. And if you have, at this part of this lecture, if you have forgotten why multiplication of Kb by the Avogadro constant gives you R, please look at the beginning of this lecture, where I have used the same equation. Okay, so now this is the average speed. What we are left over with. Okay, I think another important quantity which should be introduced is the most probable speed, VMP. The speed which has the highest probability. So the speed which has the highest probability. So to calculate the most probable speed, we need to look again onto the probability density for speeds. So the probability density for speeds is function which contains some constant. So I would denote it rho v, so for the speed, as a function of speed, is some constant c. I don't like to take over all of this m over 2 pi kbt with me, because it's actually boring to take. The most important part of it is that I have exponent of minus mv squared over 2 kbt here, and multiplied by v squared. So if I take out all of those constants, that would give me this. So I take 4 pi and all of this m over 2 pi kbt to the 3 over 2 into a single constant, which is actually irrelevant for the definition of the most probable speed, and have the probability distribution for speeds written as this. So if I want to determine the most probable speed, that I need to calculate the derivative of this function and equate it to 0. Well, the calculation of the derivative is somewhat complicated because I have a product of different terms. So I'm going to do a slightly other thing. Instead of calculating the derivative of this function, I'm going to calculate the logarithmic derivative of this function. So that is to calculate the derivative of the logarithm of the same function. Because the logarithm is actually more simply looking function. So the logarithm of this is some constant. Again, I would call it c, because, well, this c is different from this c. It's just some constant. It doesn't matter whatever constants we have. Minus mv squared over 2 kbt, okay, plus logarithm of v squared. So we multiply this by v squared. So if I take the logarithm, the multiplication turns into summation. So instead of the v squared as a factor, we would have the 2 logarithm of v as an additional term. And if I calculate the derivative of all of this stuff, that would give me mv over kbt with this minus sign, because I have minus mv squared, plus twice the logarithm v. The derivative of the logarithm of v is twice 2 over v. And then I equate it to 0. And from this equation, I get the most probable speed. And the most probable speed is square root of 2 kbt over v. So most probable speed to kbt over v. Okay, so that's the final formula which I have derived today for the lecture. The most probable speed. And well, just for some visual purposes, I'm going to draw this probability density function for speeds, rho v as a function of v. So we have this function, constant times v squared times the exponent of minus mv squared over 2 kbt. Of course, if my velocity is small, then all of this function is determined by this coefficient. So it would look like a parabola here. But of course, I'm not going to the negative v's because the negative speed is meaningless. So I have only one part of this parabola. But as my velocity, as my speed increases, I have the onset of this exponential factor, which gives something like this. And in here, this is the most probable speed. Square root of 2 kbt over v. Somewhere further away from that is the average speed. So average speed goes here because 8 over pi is greater than 2. So if you compare these two equations for the average speed and most probable speed, so you see that you have 8 over pi, the coefficient there, and this is greater than 2. And secondly, we have a so-called, so here is the average square of the speed, but we can determine a so-called root mean square speed. Root mean square speed is the square root of v squared average. So that would give us 3 kbt over m. Now 3 is greater than 2. 3 is also greater than 8 over pi. So RMS speed, root mean square speed, which actually determines the kinetic energy of molecules, is even greater than the average speed of the molecules. So this probability function is slightly, you can say, it's slightly shifted to the higher velocities. Because as we have the higher velocity, then the number of, or the volume of velocity space corresponding to higher velocities is greater. So that's why if I look at the probability distribution for speeds, it is somewhat different from the probability distribution for components, which is a perfectly normal distribution. If you remember the contents of the previous lecture, then actually if you take Maxwell distribution, c times exponent minus m vx squared over 2 kbt, then this probability density function corresponds to a so-called normal or Gaussian distribution. Okay, it's a fully symmetrical bell-shaped function. Fully symmetrical bell-shaped function. So the probability densities for speeds and velocities look quite differently due to that exact transformation from velocity to speed.